Hello again. In this section, we will discuss about gas separation membrane. As you see in the previous lectures, in the most cases, we speak about the carbon dioxide capture, separation, air separation, oxygen purification, and others. And in this case, we can use the membranes, especially polymeric membranes. Today, the carbon dioxide capture and separation is very important because the increase of carbon dioxide concentration caused to the climate change and increasing of the world temperature. Therefore, there are many methods such as absorption, adsorption with different materials and different chemicals is used. But one of the very good processes is membrane processes. Why gas separation membrane is important? Because, as before we discussed, low hazardous material we used. In this figure, you see that the main used method for capturing carbon dioxide is amine scrubbers, absorption columns, that use the amine-based solvents for capturing, and this material is hazardous. But in gas separation, we do not use any additives. Only gas come, and before the gas stream, we have a filter cartridge for removal of particles resulted from corrosion of the tubes. And after filter cartridge with using of a compressor, in liquid we have a pump, in gas transfer we have a compressor. With the compressor we increase the pressure and we have a barrier that one gas more diffuse and another one low. And very easy method for separation of the gases from together. Low energy consumption and compact size. When you see the size of the scrubber column and the size of the membrane. Therefore, the membrane is flexible for design and need very low space and usually no corrosions. When we have solutions, the corrosions in pumps, in tubes is high, but here we know corrosions, and we also use the polymeric tubes if the pressure is low or temperature is low. Therefore, gas separation is very important, and in many industries, we want to separate 2 or 3 gases from together. For example, from natural gas, one problem in natural gas is the presence of acidic gases caused to the corrosions. And we must separate carbon dioxide and H2S from the methane. Or nitrogen removal. Presence of nitrogen in the methane increase the efficiency and heat capacity of the gases. Nitrogen is neutral, and when we want to combust the gas, the energy is reduced if the nitrogen is there. Therefore, nitrogen should be removed, H2S removed. Hydrogen recovery from ammonia in the ammonia process production. Carbon dioxide separation from syngas. Syngas is a mixture of monoxide carbon and hydrogen gas, as discussed in fuel cells. The separation is very important. Hydrogen separation used in the hydrogen storage, hydrogen fuel cell, as Dr. Daka discussed. And other many applications, such as monomer recovery. For production of the polymers, we first change the ethane to ethylene, and this reaction is not complete, and we have some ethane. We must separate ethane from the ethylene and recover for recycle. Excuse me. Recovery of different monomer from petrochemical companies is very important. Separation of the oxygen from nitrogen and many applications we can say for gas separation. The most gas separation membranes fabricated as a hollow fiber, because hollow fiber has a very high surface area and we have a high efficiency. But in some cases, we have also spiral wound gas separation, and we have also plate and frame. One companies in the world produce plate and frame gas separation modules. The usual models you see, if we have a high temperature and high pressure, we fabricate the module from stainless steel. But when we have a low pressure, low temperature, we can prepare the modules from a plastic. Based on the process, the material of the housing can be stainless steel or can be plastic. And this is a usual unit of the gas separation. You see that these are cartridge filter with different micron size. For example, 10 micron, 5 micron, and 1 micron. For separation of the solids from the inlet, because if we have one particle, only one particle can cut as a knife the membrane surface, and membrane will be destroyed. Therefore, in gas separation membranes and also in RO, very important, we have not particle in the entrance of RO and TFC membranes. Because in TFC membranes, we have a very thin layer, and thin layer can be cut with the particles. Therefore, we see we have a 3 cartridge filter with different pore size. If maybe we need to the heat, if we need to the heat, we increase the temperature, go to the pressure vessels, and separate the gas can to two different lines. And this is the real picture. This is the real spiral wound module fabricated from the Fuji film. Which now the Fuji film. What is produced before Lee? Camera. But we have only have a digital, and we do not buy the Fuji photograph slides. Therefore, the company is changed our products and changed from the photograph film to membranes, because in Bau's technique, the Fuji film produced films and changed the polymer for production of the membranes. This is a list of the membranes produced by different companies and the materials used. You see most is polyimide, cellulose acetate, polyimide, polyaramide. Aramide means that aromatic amide. And the application and the module type, hollow fiber, spiral wound, and one is plate and frame. Therefore, we can use for separation of the hydrogen from monoxide, hydrogen from nitrogen, methane, oxygen from nitrogen, separation of carbon dioxide from methane, and others. In the fabrication of the gas separation, we discussed to lecture about the fabrication of the membranes. Both porous and non-porous membranes can be used in the gas separation. Both mostly use the non-porous one, and the mechanism is solution diffusion. But we have both porous and non-porous, and we have a prepare with a phase inversion, with the interfacial reaction, with the growth of the nanoparticles on the membrane surface, that we discuss all of these methods. About the mass transfer in the gas separation, we have two membrane type, porous and non-porous. If we have a non-porous, our mechanism is solution diffusion that we discussed. But if we have a porous membrane, we have the molecule size and pore size, okay? The interaction between the molecule and pore size and chemistry of the polymers membrane can cause different mechanisms. If the pore size is 100 nanometer to 10 micron, or when the pore size is bigger than 100 nanometer, we have no separation. We have no separation, and the mechanism is convective flow. That means we have a random diffusion and no. Therefore, for gas separation, the pore size should be lower than 100 nanometers. If the pores are lower than 100 nanometers, the separation efficiency is related to the mean free pass. Mean free pass of the gas. Mean free pass of the gas. What means? We show this schematic. In the mean free pass, we say that is the average distance a particle travels between collisions, between heat or between collision. That means this distance is mean free pass, average pass. This mean free pass is related to the size of the gas, and concentration of the gas, okay? When we have a big gas molecule, the distance will be lower. The possibility of the collision increases. With increase of the concentration, gas concentration, this can be increased because the collision increases. If the pore diameter is less than the mean free pass of the gas molecule, we can have Knudsen diffusion. Knudsen diffusion. Mean free pass less than the pore size. In this case, we have a Knudsen diffusion, and this mechanism most used in separation of oxygen from nitrogen from the polysulfone membranes, usually. And we have a very low selectivity, but we have. In the Knudsen diffusion, we have selectivity of 1.5, 1.6, maximum 3. 3 selectivity, that means oxygen 3 times more diffused from the nitrogen. Therefore, in this mechanism, in the Knudsen diffusion, in the surface diffusion, adsorption diffusion, we have very low selectivity, but very high flux. The porous membranes have high flux, low selectivity, but in diffusion, we have a higher selectivity, but because no porosity, the flux is low. For molecular sieving, mostly the pore size is extremely small. For molecular sieving, the pore size should be 5 to 20 angstrom, maximum 2 nanometers. If the pore size maximum 2 nanometers, in this case, we can have the molecular sieving if the pore size of 2 gas molecules is very different. We cannot oxygen separate from nitrogen, but we can separate butan from nitrogen, butan from hydrogen, because have very different molecular size. There are also another mechanism in the gas separation. In this slide, show that with increasing of the pressure, mean pass is very low. And by reducing the pressure in the vacuum, it is very big. And we want to big. But we need very vacuum condition, very low concentration, and it is not possible. Okay? We usually have a low vacuum in the gas separation, and in this case, it is based on the molecular weight of the gas can be different. We have I said that other mechanisms, such as capillary condensation. In capillary condensation, when we have a vapor, vapor is different from gas. You know, we say oxygen gas, nitrogen gas, but we say water vapor. That means with increasing of the pressure, water vapor can be condensed. Okay, vapor can be easily condensed, but gas cannot be condensed in a usual condition. And for condensation, we must reduce temperature in very low critical temperature, and after that increase the pressure. Therefore, in this mechanism used for the separation of the vapor, in this mechanism, because we have a very narrow pores, when vapor want to pass from the pores, condense in the pores and change to the liquid, and in liquid, this valves cause to the blocking and filling of the pores. Therefore, we have a new barrier, and this barrier acts as a gas separation. This pores not act. Mostly this liquid condense in the pores cause to the separation. Therefore, we have also some mechanisms such as adsorption or mechanism, no here, such as surface diffusion. In the surface diffusion, we have some functional groups that can hopping the gas, give the gas from to one molecule, one functional group to another. And in this case, we can have this show. In this case, we have some functional group can increase the passing of the gas. Therefore, we have a different mechanism. I try to most say. About solution diffusion gas separation, before we discuss that we have two important parameters. First, the molecule should be adsorbed on the membrane surface, soluble in the polymer, and in the second should be diffuse. Therefore, we have a two-step, solution, diffusion. And we have a two coefficient, solution coefficient and diffusion coefficient. For some gas, diffusivity is high and solubility is low, or one gas maybe have a high solubility and high diffusivity. Generally, we have this equation for flux. When we speak about flux, we have a constant, permeability constant, and delta P as a driving force, and L as a membrane thickness. Okay? Before we discuss. This coefficient, permeability, is resulted from two coefficients, diffusion and solubility. And the selectivity is defined as the flux of gas A to flux of gas B. What happened? We have the selectivity alpha A to B is to flux A to flux B. In the lab, we measure the volume of the gas passed. Okay, that means flux, this gas in which time pass, and our area of the membrane. Flux is related to the coefficient permeability, delta P and L. We test both A and B gas in the similar condition. That means delta P and thickness is similar. Therefore, we can use permeability A to permeability B. Because the delta P can be removed from two sides. In gas separation papers, most of the students is confused about use of permeance and permeability. Permeance is the flux. Permeance is the flux of the gases from the membrane. And its unit is GPU, gas permeation unit. Okay? We say GPU, gas permeation unit. That is the volume of the gas passed from the membrane surface area in the certain time and in the certain applied pressure. Okay? This is the flux that in the gas separation we say permeance. Okay? And the unit is 1 GPU. This is the unit conversion. From the conversion of this unit together, we have this amount. Okay? The volume of the passage, for example, in 1 second, we say 2 centicubic gas passed in which pressure and how much the membrane surface. This is the permeance. But we have another unit as a barrier. As a barrier, not work. No, go to the next slide. Okay. We have another unit as a barrier. Barrier, you see, is the similar of the GPU, only have this one in the top, okay? That means barrier as present, I no discuss about this equation, not go. Close and read. Close from the slide. No work, huh? No work here. From your laptop, huh? And okay.
The animation is one second,
What is this? Setup show. And no important, I present in this form without, if go, yes, I present after launch you correct. The online can be seen now. Need to restart, I think, huh? Yes. A barrier for each polymer and each gas is a constant amount. What means? In liquid filtration, I give to a student a membrane and say that you test the flux. One student, the similar membrane, say that this flux is 100, and another student say that 200. And both can be true. But in gas separation, when two students test one gas separation membrane, cannot report different flux, different permeance. Because the permeability, the barrier of each polymer for each gas is constant. And we can find in the literature. We can find that this P box have carbon dioxide permeability of 12 barrier. If you report 13, in the paper will be rejected, your data is wrong. Because, okay. Because in the barrier unit, in the barrier unit, the permeance of a membrane in the gas can be changed because the thickness is not introduced. When you fabricate one student 10 micron, another 20 micron, the permeance will be changed, okay? But in barrier, the permeance divided to the thickness of the membrane. The thickness of the membrane is inserted. That means we report a film with thickness of 1 micron. This barrier shows that how many gas passed from this specific polymer if they have a 1 micron. You see, we obtained GPU 100. Our membrane thickness is 20. Okay? Therefore, we divide, we multiply this micron in GPU and obtain the barrier. That means we inserted the thickness effect. You see in this, we inserted the thickness effect in the reported data, and therefore we can report a different GPU, but we cannot report different barrier. If we report, we have a problem. In most cases, students come and say that I cannot reach two reported barriers. We have a commercial polymer and the gas carbon dioxide, nitrogen. My barrier should be 10. I obtain 12. What is problem in most cases? In most cases, humidity. When the polymer absorbs the humidity of the environment, the polymer can be swell, very swell. And when we swell, we have some free volume, increase the free volume in the pores, and the flux increases. In this case, I say that keep your membrane in a vacuum oven for 1 day. And after 1 day, and before that, we give the membrane thickness. Before oven, the thickness of membrane is 20. And after 1 day in oven, vacuum oven, the thickness reduced from 20 to 17. Because absorbed many water, and this water have after that, give the similar barrier. As say, we have two solubility and diffusivity in the membrane, gas separation membrane. And we have a ceramic gas separation membrane. In ceramic gas separation, our mechanism is not send adsorption and others I discussed. But in polymeric membrane, if dense, our mechanism is solution diffusion, and this solution diffusion is related to properties of polymer and properties of the gas. One of the main properties of the gas is glassy and elastomer properties. We have the crystalline polymers, or semi-crystalline polymers, or amorph polymers that have their different behavior. In elastomer polymers, we have a flexible and amorphous polymer. That means we have 1,000 chains, and these chains can be moved easily together and is flexible. No hard interaction between the chains. But in the glassy polymers, we have a rigid and non-flexible and hard. That means we have a hard and strong interactions between the chains, and the movement of the change is very, very low. And we have a crystalline behavior. That means we have a crystal units and we have an interaction between the chains. Mostly when we have a hydrogen bond between the polymer chains, we have a semi-crystalline property. This crystallinity reduces the flexibility, and when we prepare a membrane from glassy polymers, we have a rigid pores. And the pores are not changed, the figures. But when we have an elastomer polymers, when a gas pass from the polymer chains with pressure, the pressure can be changed the pore size. And therefore, rigid polymers can good selectivity, low flux, but elastomer polymers have a bad selectivity, bad diffusion, and higher flux. We have a TG, glass temperature, and melting temperature. When we have a glassy polymers, such as this is rigid. But when we heat this in a temperature, this will be flexible, not melt. Melt is liquid. Not melt, but can change the form. The temperature that a rigid polymer can be deformed, it is the glassy temperature. That means in the bottom of high temperature, the polymer is flexible, and in lower than, it is glassy, such as glass and rigid. Therefore, the performance of a gas separation membrane is very, very related to the temperature. In a liquid membrane with increasing of temperature from 25 to 30, no any change in flux, 1%, 2%. But in gas separation, the temperature is very important. With increasing of 5 centigrades, maybe flux 3 times, and rejection will reduce. Therefore, in test of the gas separation membranes, we should control the temperature. Only experiments, only our test equipment should be inside of an oven or should be immersed in water, as discussed afternoon. Therefore, we have a different behavior. The elastomer polymers in the ambient temperature, in the atmospheric temperature, is top of the glass temperature. Elastomer TG is minus 10 centigrade. That means in the 25 centigrade located in this area and have a flexible behavior. Based on this discussion, we have 2 parameters. Diffusion coefficient, you see in this axis, we have diffusion, and in the next slide, we have a sorption coefficient. We have 2 different coefficients, and one discuss about. This diagram discuss about diffusion, not permeability, only diffusion, not solubility. In the diffusion, we have a PVC as a glassy polymer and natural rubber as an elastomer polymer. And compare the diffusion coefficient with van der Waals molar volume. That means when we go to the right, the molecular weight increases. We see when we have a rigid and glassy polymers, we have a better selectivity. The polymer, the membrane can be differ between 2 gases. For example, when we compare the hydrogen, our course about hydrogen, with nitrogen, the diffusion coefficient difference is about 100 times. Our diagram is logarithmic. The selectivity between hydrogen and nitrogen, this is about 2 and about 100 times. That means PVC selectivity for nitrogen and hydrogen is 100. But when we use the natural rubber, nitrogen here, hydrogen here, only we have a 10 times from diffusion view, okay? If we use this natural rubber, our selectivity is 10, but when we use this, maybe selectivity will be 100. Therefore, from diffusion view, the PVC is good, okay? With help of these diagrams, we can select good polymer for our separation, okay? But we see here that the diffusion of nitrogen is very higher than here. When the molecular size increases, the diffusion rate very sharp reduced. Therefore, the PVC, our glassy membranes, have a lower permeability but higher selectivity from diffusion view. This schematic shows that if our polymer is flexible, is elastomer, by passing of the gas, the chains can be change our configuration and therefore do not good selectivity because the pore size can be changed. The free volume can be changed. But in the solubility coefficient, we say that the solubility coefficient is an interaction, not diffuse. In this case, with increasing of the molecular weight in both polymer, the diffusion is reduced because the lower molecule rapid diffuse. But in sorption coefficient or adsorption coefficient, the big molecules usually good adsorb. Where we compare methane with butane, methane have 1 carbon, butane 4 carbon. 4 carbon can better interact with polymer, okay? We have this polymer, we have a 1 point for interaction, but we have a 5 point. When we have a 5 point, the interaction is high, and therefore, the adsorption coefficient is high. And you see in this case, with increasing of the molecular weight, with increasing the size, the sorption coefficient increases, okay? Also, say this with compressibility and say that with increasing of molecular size, molecular weight, the boiling point increases. Methane is gas, ethane gas, propane gas, butane is liquid, paraffin is solid. That means with addition of the carbon to the molecular structure, the boiling point increases and the compressibility increases. When we have a pressure and we have a high compressibility, that means high boiling point, in the membrane pores, in the membrane free volume, the gas can be changed to the liquid and good adsorb. Therefore, in some papers discuss about compressibility and say that this is have liquid properties, but methane have gas properties. Therefore, this would easily adsorb, and therefore solution diffusivity is high. Therefore, we have a reverse behavior. In this case, where is the Panton? Here. Panton have a very low diffusivity, but in this case, have a high sorption. Therefore, we cannot use these two diagrams separately. We can merge them, and after the merge, solubility in diffusivity. We say solubility in diffusivity is permeability. Okay? Okay? Forget, I come back. Here we say that permeability is diffusivity and solubility. Everybody is hungry. This is a diffusivity and this is solubility. Therefore, this is the sum of solubility and diffusivity as a permeability. In handbook, in gas separation handbook, we have these diagrams for all all polymers. Okay? When we have a thin film of polymers, no porosity, we can use these diagrams for prediction of the permeability. And therefore, when we have, this is the polysulfone, in the temperature is very important. You see the temperature. With change of the temperature, this data is changed. Therefore, there are tables, the permeability change with the temperature. In this temperature and with this polysulfone, the permeability as a barrier is this amount. And we cannot report another data. If we cannot, our paper is rejected. Okay, with having of this, if we want to separate the methane from nitrogen, we see that polysulfone is not good because have similar permeability, and therefore we have not selectivity. But if we want to separate methane from nitrogen, we see that the PDMS is good. Therefore, we can use of these diagrams predict the separation. You see in these diagrams that the most permeable gas is water. When we have a mix of the gases, the water will be passed rapidly because both good condensability and have a very small size. Therefore, when we have a mixing of the gases, first the water will pass. For glassy polymers, we have this behavior: helium, hydrogen, ammonia. See here, monoxide is big or carbon dioxide. Monoxide is big or carbon dioxide? Carbon dioxide is bigger, but carbon dioxide has rapid diffusion because have two functional group. Monoxide, one interaction place, but carbon monoxide have two interaction. Therefore, solubility parameter of the carbon dioxide is higher than the monoxide and have a higher diffusion rate. Okay, I pass. The reported selectivity for the different gases. In the lab, we mostly test the gases separately. We have one membrane, first pass carbon dioxide, and after that we pass nitrogen and obtain the permeance and calculate the permeability and others. But in the ideal, we have a mix of the gases. Why we do not use the mix of the gas in the lab? Because the measurement of the mix of gas need the gas chromatography, and in many labs, no gas chromatography. Therefore, report the ideal selectivity. But when we have a real selectivity, we see that when we have a mixture of the gases, the gas could interact with together, and one gas, when adsorbed, can block the active sites. And therefore, we see that the selectivity for pure gas can be changed in the presence of the other gases. But it is better we mix the mixed gas for true data. But for report of the barrier, we use the pure. But for report of the selectivity, it is better we use mix of gas. In the liquid membrane filtration, MFUF and other, we have a fouling. That fouling causes to the reducing of the performance. In gas separation, we have also the fouling. But usually do not say fouling. In this case, say aging or plasticization. The similar to the fouling, the selectivity and permeance of the membrane change during of the time. One property is plasticization. Plasticization, that means that in the first new membrane, we have this structure, this compaction. After 1 year, because of some impurities, some adsorption of gas to the polymer chains, the free volume between the chains is changed. Between the chain is changed. Okay? Change. And therefore, we usually that after the certain time, the flux increase. The flux increase and the selectivity reduce. After this time, 2 months, 3 months, 1 year, we say that the membrane have plasticized and changed the properties of the membrane. The membranes will be brittle. Membrane was flexible relatively, but after 1 year is very brittle and the properties is changed. With addition of nanomaterials, in this case, increase the long life and reduce the plasticization. The insertion of the nanoparticles can interact with the polymer chains and do not allow to interact with the gas. Mostly carbon dioxide causes to the plasticization. And another is aging. In the aging, we have a reduce in flux. Reduce because when we use the polymer as a thin layer and we have a pressure, in the gas separation, we have in most cases high temperature and high pressure. This compress the polymers during the time, and after 1 year, the pores and the free volume reduce to this one and cause to the reducing the free volume and the flux. And in this case, you see after this hovers, the membrane is brittle and destroyed. And as a final slide, in the gas separation, we have a Robinson boundary, or Robinson bond, that shows the barrier and selectivity, permeability in selectivity. We know with increasing of flux, increasing of permeance, the selectivity reduces. And we have seen that we have this bond. This one is the previous or old Robinson bond, and the right is the new Robinson bond. When we research in the lab, the best membrane is that located in the right of this bond. If we prepare a membrane and have the selectivity and barrier permeance, and our membrane based on this selectivity and permeance, if located here, it is not good, will be rejected. Because say that your membrane should be in the upper of this band. This blue locations is good. If we can prepare a membrane with high flux and high rejection, this area is ideal, is very good. Therefore, in the gas separation, most of literature you see reported here, this is a very bad, low flux, low rejection for carbon dioxide from methane. And we have this Robinson bonds for different gases, for oxygen, nitrogen, carbon dioxide, hydrogen, and others. This is also the similar diagram for reverse osmosis membrane. The rejection of reverse osmosis related to the flux, and we have a good membrane should be located in this area. There are new polymers in the fabrication. In the previous slide, you see traditional one, but every day new polymers synthesizes and report for fabrication of the membranes, such as polymers of intrinsic microporosity, which is very important and have a very high flux. That means there is some free porosity, microporosity, in the structure of these polymers. You see, this intrinsic, we have some free volumes in the polymer structure, and these free volumes increase the flux. Okay? And this is a very expensive polymers for research. Thank you. I don't know. Have any question? I will rapidly discuss about the gas separation. It's a very interesting area, but need a good equipment for testing of the membranes. Everybody is hungry.
So it was very nice, and I'm sure the students, they had all their questions answered. That's why they did not ask anything. And that we'll see, they will test it tomorrow. Do not worry how much they understood. Anyway, thank you so much for your lecture. And so please join us for lunch in 312. The lunch is ready. And we'll meet after, so what is the time now? 1:45. So we'll meet around 2:45. Okay, after 1 hour. Okay. Thank you so much.